Let's start our today's seminar, and we are happy to have Alexander Soibelman. I am twice as happy to have him here, to see him currently at IHES. Title is Motivic invariants for moduli of parabolic Higgs bundles and parabolic connections on the curve. So please go ahead.
Right, thank you. So thank you for giving me the opportunity to give a talk. And yeah, I'd like to start out by saying that this the contents of this talk is all based on joint work with Roman Fedorov and Jan Soibelman. So to sort of give a brief introduction to what I'm going to be talking about, I'd just like to start off by giving a few sources of motivation for this work. So essentially what we're trying to do is we're trying to compute certain invariants for moduli spaces, or in fact, moduli stacks of Higgs bundles or vector bundles with connections on a curve. And so sort of have this threefold motivation. The first source is coming from these Motivic Donaldson-Thomas invariants, developed by Constellation Soibelman for these three Calabi-Yau categories, and then also Joyce and Song for viewing categories of coherent sheaves on Calabi-Yau threefolds. And so what we're trying to do is do these kinds of Motivic Donaldson-Thomas invariant computations for certain two Calabi-Yau categories. And so the second source of motivation would be the work of Hausel, Letelier, Rodriguez-Villegas, and many, many others regarding mixed Hodge numbers for character varieties. And a lot of this computation for Motivic classes or Motivic invariants is related to that. And finally, the third source of motivation, which is sort of going to be my starting point for this talk, is going to be point counting of algebraic varieties and algebraic stacks over a finite field. So specifically, there are some computations done by Mozgovoi, Schiffman, Mozgovoi and Schiffman together, and also Mellet, which is sort of the another source of inspiration since it deals directly with computations for Higgs bundles. Right, so to begin, just sort of a brief introduction to point counting, or rather, I guess, a few simple examples of point counting. So we're interested in things related to counting rational points of an algebraic variety over a finite field of Q elements. So here are some elementary examples you might have already seen before. So for example, if you have some sort of n-dimensional vector space or affine space AN, you just easily count up the number of elements in that as just Q to the n. If you have n-dimensional projective space, you can just decompose that into a disjoint union of affine cells, one in each dimension up to n, and then just add up the number of points in each cell to get that the number of points in Pn is just 1 plus q, and so on and so forth, plus q to the n. And for GLN, it's also not terribly complicated. You can just think of this as a space of linearly independent column vectors, and you can try to figure out, well, how many ways can you get one linearly independent column vector, which is just any non-zero vector, so that's q to the n minus 1. How many ways can you get two linearly independent column vectors? That's just one non-zero vector, and then anything linearly dependent from that, so it's q to the n minus 1 times q to the n minus q, and so on and so forth. So you get a product like this to give you the number of points in GLN. And using that computation, you can get the number of points in the Grassmannian, which is sort of the final example that I want to write down here. You could just look at the Grassmannian as a single orbit of a GLN action. So it looks like the disjoint union of a bunch of cosets of the stabilizer. So you can, in fact, just compute up the number of points in stabilizer, since it's just the product of two GLNs times the matrix algebra, and then take that and take the number of points in GLN, divide one by the other. And so you get the number of points in a Grassmannian, and instead of writing down sort of this very messy formula, you can clean it up and write it as this Q binomial coefficient that uses these Q factorials like this. Right, so this is sort of what you're doing for varieties, but if you want to talk about stacks, then it's a little bit more complicated. So to start off with, you can think about this point counting for p to the n in a slightly different fashion. If you think about p to the n as sort of a quotient by a group action, so you can take punctured affine n+1 space and then act on it by GL1 just by identifying all the points on a line going through the origin together. And instead of doing the computation by decomposing into cells as mentioned previously, you can instead compute up the number of points in this punctured affine n+1 space, which is q to the n+1 minus 1, and divide that out by the number of points in GL1, which is q minus 1, and you get the same answer. So for algebraic stacks, it's a similar sort of thing, but now the quotient is bad in the sense that the result of the action of the group isn't necessarily a variety, but some more complicated object. And so I don't really have time to give an introduction to what algebraic stacks are, but you can just sort of think of them as some generalization of varieties where the points now have automorphisms that are non-trivial. And so the standard examples that care about as far as these computations go are sort of the quotient of the action of an algebraic group on an algebraic variety where the action isn't free, or looking at moduli of objects where you're not imposing some additional conditions like stability to make them into moduli spaces. So if you're just looking at vector bundles of, say, fixed rank and degree over a curve without stability, then you end up with something that's not a moduli space anymore. So for a moduli stack or an algebraic stack, then you can also try to count up the points in this. Going to be calling this volume. It's also called mass. So the idea is if you have an algebraic variety, you can count up the number of points just by summing up over all the rational points and counting those with weight 1 and adding them all together. Well, since there are now automorphisms of each point that are non-trivial, I'm just going to do the same thing, except that I'm going to weight each point with the weight 1 divided by the number of points in the automorphism group. And so you can add all of these together and get some sort of sum. But again, isn't necessarily guaranteed to converge, although for sort of all the cases that we care about, which are all these stacks of finite type, it does end up converging. And so to give an example of this kind of computation of volume for an algebraic stack, I'm just going to look at a quotient stack. That's going to be the quotient stack of the variety of n by n nilpotent matrices with the sort of standard conjugation action by the group GLN. And so in this case, the points of this quotient stack should correspond to orbits under the conjugation action. And that means these orbits are going to be classified by a Jordan normal form. And the Jordan normal form for a nilpotent matrix is itself classified by a partition of the number n. So then just to fix the notation, n sub lambda is going to be my Jordan normal form, and then script n sub lambda is going to be the corresponding conjugacy class, and the automorphism group of this Jordan normal form is again only dependent on lambda, and it's just going to be aught lambda. So you can do this kind of computation by just summing up over all of the possible conjugacy classes, so all of the possible partitions of n. And since you can count up the number of points in a given conjugacy class in the same way as for the Grassmannian, just by sort of looking at the cosets, then you end up with this kind of formula where the number of points, or rather the volume of this quotient stack, is just going to be the number of points in the entirety of this variety of n by n nilpotent matrices divided by the number of points in GLN. And so this is where this formula involving Q comes from. The GLN part's already been computed, and it turns out that the number of points in this nilpotent cone, or this variety of nilpotent matrices, is just going to be Q to the dimension of the variety. So it's Q to the n times n minus 1 over 2. You can take this formula and sort of transform it, write it down in a different way using a generating function. So you can write down this generating function n of t, where the coefficients are just going to be the volumes of the corresponding quotient stacks. And you can write down this formula, which you get just by dividing out the power of q from the top and the bottom. And you can transform it into a sort of more compact notation using something called the plothistic exponential, which is, there's a general construction for this sort of combinatorial, but if you haven't seen it before, then you can take what's written down here as the definition, since it will end up showing up later in some of the later computations. And so just to note, this plothistic exponential that you see here also has an inverse, which is the plothistic logarithm, and that's also going to show up. So just to warn you ahead of time. Right, so there is a more complicated example which involves computing the volume or the number of points in the moduli stack of vector bundles on a curve. So here X is a smooth projective curve of genus G, and Bonar dx is just going to be the moduli stack that parametrizes isomorphism classes of vector bundles with rank R and degree D on the curve X. And so there's this very nice formula called the Ziegel formula, where you can compute the volume of this stack over FQ in terms of the number of points in the Jacobian of the curve, and also this Hasse-Weil zeta function, which is defined in terms of some numbers of points of the curve, or on the curve over field extensions of FQ. And so this particular way of writing it is not what I'm going to be using later, but instead I'm actually going to be rewriting this zeta function in terms of the number of points over FQ and the symmetric power of the curve, like this. And so one sort of interesting thing to note about this formula is that you can see that even though this is the moduli stack of bundles of fixed rank and degree, the degree part of this doesn't really show up in the right side of the formula. So sort of independent of degree in a certain sense.
Is there any conceptual explanation why it doesn't depend on degree, or it's a result of the answer? I mean, it's just seen a posteriori.
Yeah, I think it's just sort of seen yeah after the fact. But yeah, I don't know if there's a conceptual reason.
Okay.
Right. So I want to be able to do these kinds of computations, but more generally. So instead of working in the context of computing the number of rational points in an algebraic variety over a finite field, instead, I'm going to be looking at computing or doing computations in the Grothendieck ring of varieties. So I will be introducing that next. Again, this is going to sort of be pretty standard, but the idea is that you can write down this Grothendieck ring of varieties that carries certain geometric information about these things, and it's as a group, as an abelian group, generated by isomorphism classes of varieties over a field K, subject to these kinds of cut and paste relations or scissor relations, where you're able to cut out closed subvarieties from your variety and get this kind of additive relation. So cutting out a closed piece and then adding that together with the complement should give you the entire thing. And so this is going to have a ring structure just by using the Cartesian product. And then there's also a unit element where you're just looking at the class of a point. So that's the unit. And so when I talk about Motivic classes or Motivic computations, I'm talking about this computations in this Grothendieck ring. And so again, I'm not going to talk about too much about particulars of this Grothendieck ring. Just like to mention that this is, in fact, there's this nice theorem by Francesca Bittner that says that this ring is generated as an abelian group by classes of smooth connected projective varieties in the characteristic zero case.
This is because there is a resolution of singularities.
Yes, yes, that's exactly it. It uses resolution of singularities. So right, so instead of doing this kind of point counting, going to be instead trying to think of this point counting as a realization of something in the Grothendieck ring. And so what I mean by that is I'm going to be viewing point counting as a morphism between the Grothendieck ring and the ring Z. And so the idea is that you can sort of do this in general, where you have some nice enough invariant that takes values in a commutative ring, something that sort of respects this additive or the scissor relation property. And you can try to do the same kind of thing even when we're not dealing with point counting. So basically, if you have some sort of invariant, you can, it's nice enough, you can define a ring homomorphism into the corresponding commutative ring A, and depending on the invariant, depending on the A, you get different homomorphisms. So point counting is one example, but other examples include the Euler characteristic. So if you just take Euler characteristic for cohomology, you end up with something, say in the case where case C, you end up with something that is also a realization and sort of more relevant to sort of the work of Hausel and others as co-authors and others is this Hodge-Deligne realization, where you're sending each class of a variety over K, where again, K is going to be C, to the corresponding Hodge-Deligne polynomial.
I think sometimes such invariants are called measures, like Motivic measures.
Yeah, I've also,
additive with respect to disjoint union and multiplicative with respect to Cartesian products.
Yeah, indeed. So I want to be able to do these kinds of things again, and not just in the context of varieties, but also in the context of stacks. But you can see that in the context of varieties, a lot of the methods that I use for point counting in the finite field case also end up working out pretty well to give computations in the Grothendieck ring as well. So you can see that all the formulas I wrote down previously for counting rational points are just as valid if you replace Q with the Motivic class of the affine line, and you end up with sort of the same results. You get the same formulas. And so trying to do this for varieties a lot of the time is just going to be basically trying to cut up the varieties into nice enough affine spaces, into unions of nice enough affine spaces, and then counting up the number or counting the Motivic classes of these affine spaces and putting them all back together using the scissor relations. And so I'd like to do the same kind of thing for algebraic stacks, but there's several problems with that don't really occur when you only care about counting points. And so one problem is that now points have automorphisms, and dividing out by the automorphisms, as in the case of a volume of a stack over a finite field, might no longer be possible because you can't invert the class of the automorphism group in question. So I'm going to be talking about this, or how to get around this sort of in this very limited case where essentially my stack can be broken up into pieces that all look like quotient stacks by the action of the group GLN. But in that case, and for nice enough stacks like that, it's possible to still define what the Motivic class is in something that at least comes from the Grothendieck ring. So Again, dealing with algebraic stacks is again tricky because of points having automorphisms, and again, everything is a little bit trickier because when you're counting points over a finite field, you can just add up, just take the summation over all the points of a variety and add them all up together. Whereas for Motivic classes, the class of a variety is no longer necessarily equal to the class of all the individual points added together. So in the case of just a quotient stack where a variety is acted on by the group GLN, I can try to, analogously to the finite field case, try to define the resulting Motivic class as just the class of the variety divided by the class of the GLN acting on it. And so in this case, I am having to divide by the class of GLN, and 1 over the class of GLN is not going to be in my Grothendieck ring. So I, instead of doing computations in the Grothendieck ring, have to do computations in some sort of completion where I can actually get this class of GLN to be invertible. So I take a completion of the Grothendieck ring with 1 divided by L adjoined to it, and this is essentially going to let me be able to treat 1 over L as a small parameter and get that the inverse of the class of GLN is going to be a convergent series.
Yeah, but you can add inverse to all Motivic classes of GLN without completing, yeah, like infinite. I mean, if you have a ring and whatever family of elements, you can declare them to be inversible if they are not zero divisors. So you can add 1 over the motive of GLN for all n. Yeah.
Yeah.
Yeah, I mean, it's then you don't have to complete. When you complete, you consider infinite series. And if you add inverse to some elements, you don't have to. I mean, it's maybe it's a bit stupid idea, but it's possible.
I mean, I think it's easier to work with the completion because I mean, it's not necessarily those are not necessarily going to be the only series I would need to converge.
Right. Mm-hmm.
So adding just each individual GLN is it's not necessarily sufficient for the kinds of computations that what we're going to be doing.
Okay.
But in any case, for nice enough algebraic stacks that are stratified by these kinds of quotient stacks, where you're again have a variety acted on by a GLN of some sort, you can try to define the Motivic class as just the sum over the Motivic class of the quotient stacks. And if everything is again nice enough, then it ends up that you get something convergent and independent of stratification, which does happen in the examples that we're going to be looking at. So just to look at one example before I start talking about Higgs bundles, and that is this Motivic version of the Siegel formula, which is due to Behrend and Dillon. And so essentially it looks very similar. I'm interested in this Motivic class of the moduli stack of vector bundles on a curve. And you can get more or less an equivalent formula to the Siegel formula just by replacing all the q's with l's and then replacing the number of points in the Jacobian by its Motivic class and replacing the Hase-Veil zeta function with the Kapranov-Motivic zeta function, which, as you can see, is defined in terms of the Motivic class of the nth symmetric power of the curve x. And so everything else sort of ends up working out, and you end up with the same formula, more or less. So What we're interested in computing is Motivic classes for moduli stacks of Higgs bundles and moduli stacks of vector bundles with connections. So I will briefly, again, introduce what Higgs bundles are. So just, again, we're looking at X is going to be everything is over a curve. So X is a smooth projective curve of fixed genus. And so just Higgs bundles are going to be pairs of a vector bundle and a Higgs field, which is just going to be no linear morphism of E to E twisted by the canonical bundle. So you can further twist this by some additional line bundle and get detwisted Higgs bundles. As a generalization. So same kind of thing. Higgs bundle is just a pair E and phi, where phi is going to now be a morphism into E twisted by canonical class that's twisted in addition by the divisor D. And so if we're interested in trying to look at moduli spaces of these objects, then there is a notion of stability that comes from extending slope stability from vector bundles to Higgs bundles. And so the definition is pretty much written over here entirely. So the idea is that if you have a vector bundle or a Higgs bundle, then essentially, if you have a proper subbundle F inside of that vector bundle, then that's preserved by the Higgs field, then there needs to be this kind of inequality on the slope, so on the degree divided by rank, in order for there to for it to be considered stable. So, and then if the inequality is non-strict, then you get semi-stability. So now, if you're looking at the corresponding moduli spaces, so the moduli space consisting of equivalence classes of semi-stable objects, I'm going to be denoting that by this MSSXDRD. So these are the objects of this are going to be polystable Higgs bundles, essentially, where E has a fixed rank and degree. And so for the Motivic class, there is this nice conjectural formula by Mozgovoy. And so this is done in the case where the divisor D has a degree at least 2G minus 2, where G is the genus, and where the rank and degree are coprime, meaning that the stable and semi-stable objects coincide. So this is given in terms of some generating functions. So there's a generating function, intermediate generating function for a script h lambda p of t, which is written in terms of the Kapranov zeta function z sub x. And so this is written like this. You're taking a product over all of the boxes inside of the Young diagram corresponding to the partition lambda. And then there's some additional combinatorial data coming from this partition or the box in the partition. There's arm length AS, just the distance from a given box in the Young diagram to sort of the edge horizontally. There's the leg length, which is sort of the distance to the bottom, and the hook length, which is sort of the size or the number of boxes in the hook where the given box S is a corner.
Where is the definition of this HPR? I do not see them. I see exponent of something which does not depend on PHR. Maybe P is missing.
Yeah, that might be actually a typo. Yeah, thank you.
Okay.
Yeah, there should be a P in that. Yeah, thank you. I'll fix that. Yeah, so the definition for HPR of T, which is actually what gives you the Motivic classes of the moduli space, is given again in terms of a generating function that is defined in terms of the script H. and the plethystic exponential mentioned earlier. So there's a formula here, which is correct if you add in the p in parentheses on the left side.
Yeah, but still there is a question, because it looks like, again, nothing depends on the degree in this conjecture. I'm trying to find where this h lambda, curly h lambda, they do not depend on the degree.
Yeah, as far as I know, again, it doesn't explicitly show up.
So, but it's similarly to just to vector bundles, yes. So the
Yeah.
answer does not depend on the, at least conjecturally doesn't depend.
Right, right.
Okay.
So you could do this computation, or you can get these Motivic classes from this formula, again, just by plugging in t equals 1, and then multiplying by 1/2 the dimension, L to the power 1/2 the dimension of the moduli space, which is what you get here at the bottom. And so just before I go on, I want to talk about, I just mentioned some results related to this conjecture for computing volumes of this stack of semi-stable Higgs bundles over a finite field. So some previous computations, again, that are sort of inspirational to our work, coming from Mozgovoi and Schiffman. So they had a different formula from the conjectured one by Mozgovoi for the moduli stack of semi-stable twisted Higgs bundles. So this computing number of points, or rather the volume of the stack over a finite field. And so in the case where the bundles are not twisted, so it's just sort of the standard Higgs bundles, Mozgovoi and Schiffman's formula was proved to be equivalent to the Mozgovoi conjecture in the finite field case by Mellet. And then he also extended the computation for semi-stable parabolic Higgs bundles. So looking at the moduli stack of semi-stable parabolic Higgs bundles on a curve. And then finally, in 2019, Mozgovoi and O'Gorman proved that the Mozgovoi conjecture is true in the case of volumes, so in the case of number of points over a finite field. And so what our results are concerned with are the Motivic versions of this Mozgovoi and Schiffman computation and the Mellet parabolic computation, trying to do things in this kind of generalized Grothendieck ring. So again, just to sort of fix some notation and also introduce the other object of interest. So we're interested in computations for Higgs bundles and also for vector bundles with connections. So when I mean a connection, what I mean is I have a vector bundle on a curve, and everything is going to be done in characteristic 0. And my connection is just going to be this k-linear morphism satisfying the Leibniz rule. So k-linear.
Is it spelled with T or without T?
It is spelled with T, with the T. I actually double checked this specifically because I misspelled it previously. Yeah, so this, and then the sort of objects in play here are going to be these moduli stacks of connections on the curve X. And so con Rx is just going to be the moduli stack that parametrizes up to isomorphism of these pairs of vector bundle with connection nabla, and the vector bundle is rank R. And so for the moduli stack of Higgs bundles, we're looking at semi-stable Higgs bundles. So that slope stability condition that I mentioned earlier is in play. And then it's, again, moduli stack of Higgs bundles that have vector bundle with fixed rank and degree and satisfying the slope stability condition or slope semi-stability condition.
I'm just checking Wikipedia, it's without T. Maybe it's a different Leibniz.
Okay, so that's even more embarrassing because I specifically double checked this.
All right. So anyway.
But yeah, I'll look it up again after the talk. Yeah, so the idea is that you can relate the Motivic classes of connections and Higgs bundles together in the following way. So essentially, the class of the stack of connections on a curve is just going to be the same or equal to the class of the stack of semistable Higgs bundles for degree 0. So you essentially get some nice existence condition that lets you, for connections on these vector bundles, that lets you relate the two together. And so then the sort of exact computation or the sort of explicit formula you can get for the class of the moduli stack of semistable Higgs bundles comes from, again, or comes through several generating functions. So we're in everything that happens sort of in all of our computations, we're dealing with the case where the characteristic of the field is 0. And then you can write down a generating function that actually generates these classes of the stack of semistable Higgs bundles in terms of these intermediate BRDs, which are themselves actually defined in terms of another generating function. And so there are already 2 generating functions on this page. And unfortunately, if I explicitly defined everything that goes into defining the BRDs, then this would take at least 2 more slides. So I am not going to do that. And if there's any interest at the end of the talk, then I'll try to display the full formula.
Yeah.
But the whole, sorry?
Actually, here, differently from Mozgovой conjecture, which is still conjecture. Yeah.
Yes, as far as I know in the Motivic case, yes.
Yeah, it's not obvious that the answer doesn't depend on the degree.
Yes, so as far as I know, all that we have is that it's periodic in a certain sense, that you can add these multiples of the rank to the degree and get the same thing, but yeah, not wholly independent.
Okay.
So yeah, so again, this formula for this BRD is given in terms of, explicitly in terms of this J lambda motivic and H lambda motivic, which are themselves rational functions that are expressed in terms of the Kapranov motivic zeta function. So that's sort of as far as I'm going to describe them, at least at the moment. And then the exponential and the logarithm that are found in these formulas are the plothistic exponential and the plothistic logarithm. That I've again mentioned earlier. So I want to talk about the parabolic case of these computations next. So to do that, I want to introduce what parabolic bundles are, and then talk about the corresponding parabolic Higgs bundles and parabolic connections. So parabolic bundle is just going to be a vector bundle together with some additional data. So namely, I'm going to be fixing some number of points on my curve X. So that just means I'm fixing a reduced divisor. And then the additional data is going to consist of flags inside of the fiber at each one of the fixed points. So there's a filtration of the fiber by subspaces. And to fix notation, I'm going to be fixing the dimensions of all of these subspaces in the flags and putting them together into a vector gamma, which is the dimension vector of this parabolic bundle, bold E. And so then, just as with the vector bundles, you can try to introduce the notion of slope to get a slope stability condition. And to do this, for parabolic bundles, there is an additional parameter. So that goes into the definition of degree. So once again, I want my slope to be degree divided by rank. And the rank is the same as the old rank. So it's just the rank of a vector bundle. But the degree is more complicated. It's going to involve the degree of the vector bundle plus an additional term that depends on this new parameter sigma. So there's some additional parameter sigma, which is just going to be a vector of real numbers, and these are going to be weighting up the dimensions of the quotient spaces of the adjacent vector spaces in this flag, or in each of the flags. And I'm doing this in a slightly non-standard way, talking about kappa sigma degree instead of just parabolic degree. So for parabolic degree, as you can see on the slide, the kappa is equal to 1. So it's just the vector bundle degree plus some correction depending on the stability parameter. But I'm introducing this in terms of kappa because this kappa sigma degree shows up in a little bit different context in one of the formulas later on. And it actually has to do with an existence condition for Higgs bundles or connections that are somehow preserve this parabolic structure. So given that there is some definition of slope dependent on a parameter sigma, I can try to again introduce slope stability in sort of the same way. I'm looking at sub-objects that satisfy certain inequalities to get my notion of stability or semi-stability, so just these inequalities on slope. And now I want to also generalize what I mean by connection and Higgs bundle. So this is going to be something that somehow preserves this flag structure that's given in addition to the vector bundle to give you the parabolic structure. So to get a parabolic connection or a parabolic Higgs bundle, specifically a zeta parabolic connection or zeta parabolic Higgs bundle, I'm going to be fixing a vector of numbers, or rather entries in my field K that I'm going to be denoting by zeta, and there's going to be one for each one of these flag subspaces. And so then a zeta parabolic connection is going to be a logarithmic connection. So meaning I am allowing for poles up to order 1 at the marked points. So you get something which now potentially has residues at each one of the marked points. And the residues are just going to be going to be some endomorphisms of the fiber. So in order for the connection to be parabolic, I essentially wanted to preserve, want the residues to preserve the flags inside each fiber. And for it to be zeta parabolic, I want it to preserve them in a specific way. Namely, I want the residue to act by zeta ij on the quotient for each one of the adjacent subspaces in the flag. And then you can give a similar definition for zeta parabolic Higgs bundles. So just the same kind of thing. You have a Higgs bundle where you're allowing for your differential forms to have poles. So then you can also try to write down what the residue is, and the residue has to preserve the flag in a certain way. And so given zeta parabolic connections and zeta parabolic Higgs bundles, you can look at moduli stacks, parameterizing isomorphism classes of these kinds of objects, and once again try to compute the Motivic classes of these moduli stacks. So again, to fix notation, con gamma zeta xd is going to be the moduli stack parameterizing parabolic bundles with zeta parabolic connections. And I'm fixing both the dimension vector, so that fixes all of the dimensions of the subspaces and the rank of the vector bundle. And I'm fixing the zeta, which is sort of the vector consisting of the eigenvalues, if you will, of the residues of the connection at the fixed points in B. And so you can also do the same kind of thing with Higgs bundles. So I'm looking at the moduli stack of semi-stable Higgs bundles, where I'm fixing a bunch of parameters. So I'm fixing the dimension vector, I'm fixing the degree of the vector bundle, I'm fixing the vector of eigenvalues, and I'm also fixing the additional stability parameter sigma. And so fixing all of those things can talk about Higgs bundles that are zeta parabolic and that are semi-stable with respect to the stability parameter sigma. And so then there is, once again, as in the case without any parabolic structure, there's a relationship between connections and semi-stable Higgs bundles. And so this is, again, given in characteristic 0 in terms of this formula. So basically, assuming some technical condition where K is, where a field is not an extension of the rational numbers, then it is possible, given one of the vectors of eigenvalues, so for, say, the semi-stable Higgs bundles, to obtain another vector of eigenvalues for the connections, such that the corresponding Motivic classes end up being equal. And so somehow this new vector for the connections of the zeta prime comes from the old vector zeta together with the stability parameter sigma. So somehow those are combined together.
Yeah, it looks like kind of a bit formal. If D is empty, if I consider just and maybe even no parabolic structure at all, so vector bundles carry the connection if and only if it's a direct sum of indecomposable vector bundles of degree 0. So there is this André-Weil theorem. And therefore, if you want to compare connections with Higgs bundles, so then degree on the Higgs bundle side also must be equal to 0. Otherwise, these classes cannot coincide. And what here replaces this condition that the degree?
I mean, there's a shift, right? So because of the additional stability parameter sigma, there's a shift. So you can you can sort of shift it back and forth.
Yeah, but where it's hidden on the left hand side, I see only zeta prime. Does it depend on sigma?
I mean, everything. So I mean, I guess I could say that the zeta prime includes not only the zeta and the sigma, but also the d. So all of those sort of come together.
Okay, I see.
Yeah.
Mm-hmm.
Yeah. So this is, again, there's a more complicated existence condition in the parabolic case, where parabolic Higgs bundles and parabolic connections aren't guaranteed to exist. So the sort of existence condition for those have to be sort of reconciled with each other to get this equality. So, and again, you can do a similar computation for the moduli stack of semi-stable parabolic Higgs bundles, again in characteristic 0. So, which is, again, everything is happening in characteristic 0. So this is given in terms of multiple generating functions once again. So if you compare this formula to the earlier one, they are pretty similar. So the actual classes of the moduli stack of semi-stable Higgs bundles are given in terms of an intermediate generating function involving these B gamma D bars. And then these B gamma D bars are themselves defined in terms of, explicitly in terms of the generating function, which is, again, should look similar to the previous one. It involves the same J Motivic, J lambda Motivic and H lambda Motivic. And so if you sort of look at this first generating function involving the H gamma Ds, you can see that the sum is taken here over all possible dimension vectors. And you can see that part of this summation also involves this degree of 0 zeta gamma equaling to 0, which is a necessary condition for the Higgs field to even exist on a given vector bundle. But this is sort of where the kappa sigma degree went. And so the idea is, again, you get something that's very similar to the case where there's no parabolic structure, but there is an additional component to this formula, namely to the part that gives you the generating function for the B gamma D bars that specifically is responsible for this parabolic structure. And that is this additional term at the end here, which involves this H lambda twiddle, or this rather H lambda twiddle Motivic. And these are Motivic versions of the modified McDonald polynomials. So you get one of these for each one of the additional points where you have the parabolic structure. And so this is somehow sort of factors the two. There's like an additional part that's just responsible solely for the parabolic structure, and that sort of factors off from the part that's responsible for the Higgs bundle without the parabolic structure part.
I'm not sure that everybody knows what is just ordinary McDonald polynomial, maybe modified, but Motivic modified.
So yeah, there's a symmetric polynomial called the modified McDonald polynomial, and it is possible to define a Motivic version of that. But I don't know if I want to try to go into what any of these things are. But yeah, it's a symmetric function. It's a nice symmetric function.
And basically you use the fact that if you take this, whatever, K0, the ring is K0 of varieties, it resembles somehow the ring of symmetric functions. Yeah, you can take symmetric powers, wedge powers, all these symmetric operations in the Motivic ring.
Yeah.
Okay.
Yeah. So you can get this this kind of formula, and just one more thing before I talk about try to wrap up and talk about what we're currently working on. I do want to mention this sort of nice, I guess, elementary application that comes from the Dilling-Simpson problem, which is as follows. So you can pose this rather elementary problem as posed in a letter from Dilling to Simpson. And the idea is that you're fixing some number, so n conjugacy classes of invertible complex matrices, and you're asking whether you can find matrices in these fixed conjugacy classes that multiply to give you the identity. So you can try to reformulate this this Dilling-Simpson problem in terms of, again, vector bundles with connections as follows. So this actually ends up being equivalent to the following question. So if you have a again, some number of points on P1, so reduced divisor, and you have fixed conjugacy classes of R-dimensional vector space endomorphisms, then does there exist a vector bundle together with a logarithmic connection such that the residues at the marked points lie inside the conjugacy classes? And so you can
so AI will be local monodromies.
Yeah, so you can get the AIs by passing to the monodromy operators for this connection, and sort of the condition of this being punctured P1 is what tells you they multiply to the identity. So this sort of rephrases this Dilling-Simpson problem in terms of vector bundles with connections, and you can further reformulate it in terms of vector bundles with, or parabolic vector bundles with parabolic connections in the case where the conjugacy classes are semi-simple, meaning that all of the matrices are diagonalizable. So in that case, it's possible to define the correct parabolic structure, define the right flags to get parabolic connections to be just the same as, or find the right flags and the right zeta to get zeta parabolic connections to be just the same as solutions to this Dilling-Simpson problem. And so then the condition that the corresponding moduli stack has points over C is the same thing as saying that the Dilling-Simpson problem has solutions. And then the stack having points over C ends up being the same as the motivic class being non-zero. So there is a relationship between the motivic class being non-zero and then the Dillings-Simpson problem having solutions. And you can sort of continue on this on and tie this Dillings-Simpson problem further to using one of the previous theorems to the moduli stack of semi-stable parabolic Higgs bundles also being not empty and or the motivic class not equaling zero. So there's a relationship going back and forth between the two. So I want to mention that, and then to sort of finish up, I want to briefly discuss our current work, and this involves the irregular parabolic case. So this is essentially looking at Higgs bundles and vector bundles with connections where we're allowing for poles of order higher than 1. So in order to look at those, I want to introduce a parabolic structure that these kinds of things will be preserving. And this is a parabolic structure that is more general because I'm allowing my divisor D to no longer be reduced. So for a non-reduced divisor, I can define an irregular parabolic bundle, again, in terms of a vector bundle together with a filtration. But now instead of a filtration of the fiber by vector subspaces, I have a filtration of the pullback of the vector bundle to the corresponding infinitesimal neighborhood of each point by free submodules. So this is going to be giving me an irregular parabolic structure, and I can define my zeta, my vector of eigenvalues that I want to be, or that I want to somehow use to define my parabolic Higgs bundles and connections in terms of essentially these kinds of Laurent polynomials. So no longer looking at numbers, but as sections of these kind of sheaf of twisted differential forms. And so you can once again define what an irregular zeta parabolic Higgs bundle is, or what an irregular zeta parabolic connection is, in more or less the same way. I want to preserve my filtration in a particular sense. And then once again, it is possible to define what stability is for these things so that I can talk about, say, the moduli stack of semi-stable irregular zeta parabolic Higgs bundles. And so again, we want to sort of obtain versions of the two theorems that I've given examples of in the past several slides, which is want to be able to relate connections and Higgs bundles together, and then to be able to compute the motivic class of Higgs bundles in terms of maybe some generating series. But again, this is trickier in this case. So in the case of just connections on a vector bundle or a curve, there's an existence theorem, this Weil theorem for the existence of a connection. In the case of zeta parabolic Higgs bundles where they're not irregular, or zeta parabolic connections where they're not irregular, there's also an existence theorem, but there's not nearly as nice an existence theorem in the irregular zeta parabolic case, which makes relating the classes of the two things more difficult. So some nice type of existence theorem would make this work out. And then again, the computation for the actual moduli stack of semi-stable irregular zeta parabolic Higgs bundles is also trickier. So there's something that should go in the formula in place of the modified modonal polynomials, but we're not exactly sure what. So, and finally, you can also try to relate this to the Dillings-Simpson problem, but not the Dillings-Simpson problem I mentioned earlier, rather an irregular version of that. So the Dillings-Simpson problem asks about the existence of connections with some fixed normal forms for local data, namely fixed conjugacy classes of the residues. So I can ask instead whether I have a connection on a vector bundle on P1 where I'm fixing some other kind of normal form, a more general normal form, like say the HOT normal form for my irregular connection, and then ask the same question. So do there exist connections with this fixed irregular normal form? And then try to, once again, relate solutions to that question to Motivic classes or non-emptiness of moduli stacks of some sort of irregular parabolic connections. Maybe there's some relationship there. But again, I don't know. So I think that is everything that I wanted to say. Thank you.
All right, thank you very much. You're sort of on time. So Q&A session. So questions, please. Okay, there is a question in the chat from Zeta. Is the additive multiplicative Deligne Simpson completely solved?
I mean, in a certain sense, yes. So there are, I guess, multiple ways of solving it. There's sort of one way that involves some sort of quiver variety approach in the additive case, it's a straight up quiver variety approach. In the multiplicative case, it's a multiplicative quiver variety approach. But there is some condition on dimension vectors that is equivalent to solutions to the additive or multiplicative Deligne-Simpson problem, at least in the case where the matrices don't have common invariant subspaces. So yes, and there is also a sort of quiver variety approach to the additive problem in the irregular case as well.
Mm-hmm. So actually, if you want to ask a question, you can unmute yourself.
Yeah, it's easier if I can.
Yeah, it's so more questions. Actually, maybe I have a couple of comments since I'm also one of the co-authors. So first, you mentioned basically just vector bundles, but people can also consider Higgs bundles for, say, an arbitrary, say, reductive group G. So the question still makes sense. Yeah, it's about, I mean, the question about computing a Motivic class, it makes sense for an arbitrary group G. So that's.
I mean, yeah, it does. I think there are some technical problems as well. You have to sort of, in terms of what you're working in, like if you're working on the Grothendieck ring or if you're working in something else, since you need to like impose an additional condition of some local, something being locally trivializable for an arbitrary group.
Slightly different. You didn't say anything about the techniques which was used, but the technique partially it uses the structure of an additive category, or sometimes even abelian category on Higgs bundles, on bundles with connections, because in the proof we used whole algebras of these additive categories. And if the group is arbitrary, this technique doesn't work because you cannot add two G connections without changing the group G. So that's one thing. Another thing which actually I wished you to mention, although it's also sort of speculative, it's in the parabolic case, there is a very strange phenomenon that the Motivic classes of, say, it's not precisely, but in the spirit, that's what I'm saying, that if you take the Motivic class of Higgs bundles with parabolic structure and some finitely many fixed points, then it factorizes into the product of the Motivic class of Higgs bundles without marked points, which mean non-parabolic case, and some local expressions which depends only on the neighborhood, on formal disks central.
Yeah, so that's where these modified Motivic modified Macdonald polynomials are coming from.
Yeah, and this makes a link to the affine Grassmannians in this geometric Langland story, because these, for example, these strange symmetric functions, Macdonald polynomials, how they appear. I mean, it's strange why they appear in the geometric problem, but the reason is a Satake correspondence. That kind of, if you consider local geometric Langlands as equivalents of the tensor category of certain perverse sheaves on the affine Grassmannian with representations, finite dimensional representations of the Langland dual group. So there is kind of a toy model at the level of K groups of these categories. It just amounts to the isomorphism of the spherical Hecke algebra with the algebra of polynomials on the Cartan, which are invariant with respect to the Weyl group. So then for the group GLN, this means that the K group of this category of perverse sheaves supported on the orbits, on these Schubert varieties in the affine Grassmannian. So this K group is simply isomorphic to the group of symmetric, to the ring actually of symmetric functions and variables. And so Macdonald polynomials lives in this algebra of symmetric functions, and you can tell which elements of the spherical Hecke algebra, which elements correspond to Macdonald polynomials. Roughly speaking, they are sort of characteristic functions of the natural of the orbits of this Schubert variety decomposition of the affine Grassmannian. And this fact explains why Macdonald polynomials appear in relation to affine Grassmannians. And there is an old result of Lustig, I believe from 1981, and he says how to embed these nilpotent endomorphisms, which you mentioned in your talk, like if you consider n-dimensional vector space and all nilpotent endomorphisms, you can embed the thing to the affine Grassmannian of GLN. And so then if you want to consider local things, local Higgs bundles, like bundles on the formal disk endowed with nilpotent endomorphisms, then they should be embedded to the double affine Grassmannian. And so then you see there is very interesting, possibly very interesting relation to the geometry of geometric Langlands. So then kind of this is not entirely all this, this subject is not just about generalization in the direction of irregular Higgs bundles, which is actually we have no idea how to do, but also there are some other possibilities in relation to GLC, geometric Langlands correspondence. In particular, there are some interesting formulas by Chadouard and Lamont, which computes, of course, they did not consider motifs, they considered just Higgs bundle, like computed number of points over a finite field, but these are computations which use which use trace formula, which use this Arthur trace formula, some kind of integration of the space of Edel, some indeed technique of Langlands, which seems to be relevant, but this is another puzzle. In what sense that technique can be useful in computation of Motivic classes. But this is a comment, it's not a question.
Okay.
All right, so questions, more questions. Okay, another question. Can you unmute yourself and ask? At least we'll see, we'll hear your voice. So do you want me to read it? Okay, is there a Motivic analog result for the corresponding moduli spaces? Okay, regular or irregular. So if we consider probably, I'm not sure, do you mean just moduli spaces instead of stacks?
Yeah.
Yeah.
Yeah, I mean there are some results, right, for some computations. There was some computations I remember for like low rank, I think, for like there's like Garcia Prada, Heinloth and Schmidt did some computations, like in specifically the Motivic case, using this Bielanski-Brula decomposition. I know there was a computation by Doe in the parabolic case, again moduli space of these parabolic Higgs bundles. Again, also using this decomposition using this Bielanski-Brula theorem, and so those are some of the ones that I know about. There should be, yeah. I'm not sure. There maybe there's some others that if I think about it, but yeah, at the moment I'm not sure.
Yeah, but actually it's a good question, because when you have moduli space, which is a variety, not a stack, indeed you can, especially in the case when it's smooth, you have you can have the C star action.
Yeah, it's because of that. Yeah,
that's what you mean, Bielanski-Brula cell decomposition.
Yeah, it's like a Morse theory kind of thing. Yeah.
Yeah, algebro-geometric Morse theory, but for stacks, there is no analog, at least I don't know what is the analog of this Bielanski-Brula theorem. And therefore, the technique doesn't work. Actually, there is another approach, at least to Higgs bundles. You see, in our story, sort of a very rough idea was that you have Higgs bundles, which mean a bundle with some Higgs field. And so we have a forgetful morphism to bundles, just forget the Higgs field. And as you saw for the bundles, for the vector bundles, there was a formula of Berendt and Dillon for the Motivic classes. So then if somehow we are able to take care about the fiber of this projection, then we can compute the Motivic class of Higgs bundles themselves. So which means that we sort of reduce dimension from 2 to 1. From 2 because the Higgs bundle defines a spectral curve. Higgs field defined a spectral curve, and it's a curve in the cotangent bundle of the curve X. So basically you consider, say, vector bundle, like coherence shifts in the cotangent bundle on the surface, but which have one-dimensional support, which are supported on the spectral curve. So, and somehow we do not use spectral curves. We prefer to work with something of homological dimension 1. coherent sheaves on the curve. But there is a possibility to go from dimension 2 to 3 dimensions. Yeah, to like if you multiply the cotangent bundle to the curve by a line, you get a 3-dimensional non-compact Calabi-Yau. And so then you can use some other techniques. And there are papers by Diaconescu, Donaghy, and Pantev, several papers on the parabolic and also I think on the irregular case, and they are not 100% rigorous because first they go to 3-dimensional Calabi-Yaus and then they use some techniques from physics, which is not quite rigorous, but so you can go in both directions. You can have more geometry. I know that there are some David Schmolik, he worked on that, but I'm not sure whether still does. But so, I mean, if you are more geometer, kind of moral prefer geometry, then you can avoid this technique of whole algebras like this algebra and work with geometry, 3-dimensional Calabi-Yaus, and look for, it's called Pandaripande-Thomas PT stable pairs and so on, so on. So then there are possibilities. Yeah. Flat bundles. Now, next question from side. Okay, how about flat bundles? No natural. Yeah, absolutely. Yeah, I see. So he apologizes because there is a noise, so he just writes in the chat. Yeah, that's yeah.
Yeah, I don't know.
No, for start, no, it's another very interesting question. You see, if you consider a non-parabolic story, yeah, just Higgs bundles, bundles with connections, they all belong to a twistor family over CP1. Yeah, this, which is part of Simpson non-abelian Hodge theory. And so these Higgs bundles, it's a fiber at 0 of this twistor family, and the opposite, with opposite complex structure, it's fiber at infinity, sort of a fixed points of the C star action on CP1. And for any other, for any non-zero complex number, for any point of the C star, CP1 minus 2 points, the fiber is isomorphic to bundles with connections. It's what Deligne calls lambda connections. Lambda is a parameter on CP1. It's coordinate on CP1. So you can try to prove that the motive of Higgs bundle, the motivic class at the generic point, is equivalent to the motivic class, the point of the fiber at 0, using this C star action on the base of the twistor family. But if you want directly use C star action on bundles with connections, then I don't know. You should make them into lambda connections, which means that you multiply lambda d over dz plus, or lambda d, maybe in my invariant, lambda Durham differential plus a Higgs field. When lambda equal to 0, you get just a Higgs field. But you can rescale this lambda. So then you still have a C star action, which is sort of a highly non-trivial. If you transform it into the C star action on Higgs bundles, it's non-holomorphic action. But still, I mean, our approach is to prove that motives of something about bundles with connections, like stack or moduli space, whatever, bundles with connections, is equal to the motive of Higgs bundles. And then most of the work is done with Higgs bundles, where we do have cis direction. Actually, not always. If you consider non-nilpotent Higgs fields, then you cannot rescale the Higgs field because you rescale the eigenvalues. So it's also not quite a cis direction. So in particular, if you want to work with moduli spaces for Hodge, yeah, okay, good. So okay. So let me stop because I already got thank you.
Thank you.
All right. So more questions? All right. Okay, if there are no more questions, so let's thank the speaker for the very interesting talk. Okay, and this is it.